Hello everyone. So welcome you all for this lecture. So in this lecture, I'm going to explain counters, different types of counters in sequential circuits, and the working principles of the different types of counters. Okay. So before going to explain this counter, in my previous lecture, I have explained the different types of sequential circuits. That is different types of flip-flops and how to convert one flip-flop into another flip-flops. That is the basic things of this counters. Okay, so counter is one of the application of sequential circuits. So this is the introduction about counters. Counter is a sequential circuit. A digital circuit is used for counting pulses is known as counter. Yes. So for what purpose we are going to use this counter means just we are going to count the binary numbers. Okay. So we know that sequential circuits are depends upon the clock signal. Without clock signal it won't work. So each and every clock pulse. So each and every clock pulse the state will be counted. There is a clock number 1, here the state is 1, clock number 2, state is 2, clock number 3, state is 3. Like this, whenever the clock is present, the state will be counted. So for this purpose only we are going to use this count. So counter is the widest applications of flip-flops. It is a group of flip-flops with a clock signal applied. Yes. So how to construct this counter means when we are going to combine more than one number of flip-flops together, we can make this counter circuits. Okay. So in counters, there are two types will be there. One is asynchronous counter or a ripple counter. Another one is synchronous counter. Okay. Let's see one by one. Asynchronous counter. So it can be easily made from a toggle or a T type of flip-flops. As we know that for four types of flip-flops, S or J, K, D, and toggle flip-flops. So we can make this asynchronous counters with the help of toggle or D type of flip-flops. Yes. They are also called asynchronous counter because the clock input of the flip-flops are not all driven by the same clock signal. Yes, this is a very important thing in the asynchronous counter. Have a look at this. For the first flip-flop only, we are going to give the clock pulse. The second flip-flop is clock pulse is driven from the previous flip-flop outputs. This is the main thing in the asynchronous counter. Okay. So each output in the chain depends on a change in the state from the previous flip-flop's output. Yes. So each and every flip-flops have to wait for the previous flip-flop output because here the clock is connected from the previous one. So once this flip-flop is providing some output, then only this flip-flop will be activated. So this is what the introduction about the asynchronous counter. So keep in your mind, the first flip-flop only we are going to provide this clock pulse. The rest of the flip-flops are driven from the previous flip-flops output. Okay, and this is the timing diagram of this synchronous asynchronous counter. So this timing diagram part I will explain in the upcoming slides. Okay, fine. And synchronous counter. So if the clock pulses are applied to all flip-flops in a counter simultaneously, then such a counter is called a synchronous counter. Yes. Have a look at this. This is the clock pulse. They are applying simultaneously to all the flip-flops. Okay, so here the flip-flops are no need to wait for the previous flip-flop outputs because here individually we are applying clock pulses to all the flip-flops. So this is what the definition about the synchronous counter. So in asynchronous counter, for the first flip-flop only we are providing clock pulse. The rest of the flip-flops are driven from the previous flip-flop outputs. But for synchronous counter, we are providing the clock pulses simultaneously to each and every flip-flops. Okay. In the classifications of counters. So depending on the way in which the counting progresses, yes. So we know that the counting process, see, when we are counting in ascending order 1, 2, 3, 4, 5, 6, 7, this is the ascending order counting. If suppose I'm going to count in a descending order means 7, 6, 5, 4, 3, 2, 1, 0. So this is up mode counting and this is down mode counting. Okay, so that's why during the classification we can classify this as an up counter, down counter, and up down counter. Yes. So we can design a circuit. It will count in both direction, up and down direction. So for that we are in need of one control signal. For the first two counters, up counter and down counter, there is no need of control signal. But for an up-down counter, we need to use one control signal because the circuit is going to operate in both directions. Okay, so these are all the counters we see next. Right. So first one, up-down. Have a look at this block diagram. So here the output of the previous states Q and Q bar is given, and here clock pulse is given, and see this is the control. If this control is 1, then the counting is going to count in the up mode direction 1, 2, 3, 4, 5. If suppose this control is 0, then it is going to count in down mode direction. Okay. So this control signal is going to decide the entire operation of this sequential circuit. See, up counting mode when m is equal to 0. Yes, this control signal we can take any value for any kind of a direction. Okay, earlier I said 1 for up and 0 for down, but here they mentioned for up counting mode they are going to take a m is equal to 0. Yes, it's a designer choice. Okay, yes. So when it is m is equal to 0, it is going to count in the up counting mode. When m is equal to 1, it is going to count in the down direction mode. Okay, so the differentiation between this up counting and down counting is the connection between the flip flops. Okay, so see here, here Q bar output is connected, but in this Q output will be connected. Okay, see, Q output will be connected. That is, in a single flip flop, this is Q output and this is Q bar output. If you want to count in the upward direction, then this Q output will be connected to the next flip flop. If suppose you want to connect in the downward direction, then this Q bar will be connected to the next flip flop. That's the difference. Okay, we'll see it later. Right. The next thing is modulus counter. So modulus counter we can call it as a mod n counter. Here n is represent the number of states. Say for example, if I am telling a mod 4, then this counter is going to count 4 number of states. It will not count up to number 4, it will count 4 states, that is 0, 1, 2, 3. This is 4 state. Okay, if suppose mod 7 means it will count up to 7 states, that is 0, 1, 2, 3, 4, 5, 6. It will not count up to 7. Okay, total number of states is 7. Okay, fine. So see here, 2-bit triple counter is called as mod 4 counter. So 2-bit counter means it will count 4 states, that is 2-bit 0, 0, 0, 1, 1, 0, 1, 1. How many states is there? 4 states. That's why 2-bit counter is called as mod 4 counter. Then 3-bit counter is going to count 8 states. That is, it starts from 000 to 111. So that is 0 to 7. Totally 8 states will be there. Then the 3-bit counter is called as mod 8 counter. Okay, fine. So in this type of modulus counter, there are a variety of types will be there. That is, 2-bit counter is called as mod 4, and 3-bit counter is called as mod 8, and 4-bit counter is called as mod 6. So these are different types of counters we'll see in the upcoming slides. Okay, fine. And the next thing is applications of counters. Where we are going to use these counters. Okay, for frequency calculations and digital clock or time measurement, analog to digital converter, and digital to analog converter, frequency divider circuits, and triangular wave generator. In these places, we can be able to use these counters. Okay, so these are all we are going to use counter as a basic elements. Okay, fine. The first one is 4-bit asynchronous up counter. So it is always called as ripple counter. Why it is called as ripple counter means this is asynchronous, right? So as I already said, ripple asynchronous means the first flip-flop output will be connected as a clock to the second one, and second one is connected to the third one. So the first flip-flop output will be rippled to the second flip-flop as a clock, and second output will ripple to the third clock. That's why it is called as a ripple counter. Okay. So it will count up to 2 power n states. Okay, so n bit ripple counter, it will count up to 2 power n state. So here 4 bit ripple counter. So here n is equal to 4. So 2 to the power of n, which is equal to 2 to the power 4 equal to 16. So 4 bit asynchronous counter, it will count up to 16 states. That is 402 4 ones. Okay, so totally 16 states. Okay, right. So it is an asynchronous counter. Different flip-flops are used with the different clock pulse. All the flip-flops are used in a toggle mode. Yes, only one flip-flop is applied with the external clock. This is very important. Another flip-flop clock is obtained from the out of the previous flip-flop. Yes, this is what the basic requirement of the asynchronous counter, right? The flip-flop applied with the external clock pulse act as a LSB. Yes, in the counting sequence. Okay, so here see, this is a LSB and this is MSB. So the first flip flop will be connected to this position. Okay, let me explain with the circuit diagram. Fine. So have a look at this 4-bit asynchronous ripple up counter. So here I have taken a JK flip flop. So 4 JK flip flops are taken. This is a flip flop number 0, flip flop number 1, 2, and 3. So JK flip flop. So two inputs J0 K0, J1 K1, J2 K2, and J3 K3. And the outputs are Q0, Q1, Q2, Q3. Okay. So just now I told so LSB is connected at the first flip flop. Okay, so here clock is negative edge triggering is used because here one bubble is there, that is negative edge clock. And always for JK, for all the flippers we are giving the value is equal to 1 because why here the value is equal to 1 means according to the JK flip flop, when both inputs are 1, it is going to perform the toggle condition, which means each and every time it is going to change the outputs, that is 0 1 0 1 0 1 like that. Okay, fine. So here the output is Q1, Q2, Q3, and the first flip-flop output will be given to the second flip-flop clock, and second flip-flop output given to the third flip-flop clock, and here third output is a fourth clock. Okay, fine. So, and this is the truth table of the ripple counter. So let me explain this truth table. So during the first clock, that is the clock is equal to 0. If there is no clock is applied, the flip-flop it won't work. Okay, so the very first condition in sequence circuit is we need to erase the previously stored values because this is in a memory device, right? So someone has used this devices earlier. So if you want to use as a new one means, so your job is first apply the clear signal to erase everything. That's why when I'm applying this clock is equal to 0, my clear value is equal to, that is clear value is equal to 1, which means I'm going to erase everything. That is, first initially I'm going to set q 0 0 0 0. Okay, so this is what my first condition. And second condition, I'm going to apply the clock pulse. Yes, clock pulse value is equal to 1. So what will happen? See, clock is equal to 1. And now I'm going to apply this logic 1 to jk. So jk is equal to, now this is your 1 1. So what it will do? It is going to toggle the previous output. What is the previous output? The previous output is 0. So now if it is toggling means now the present output is 1. So this is 1 means this one will goes to the clock here, but this is negative edge triggering. So negative triggering means whenever 0 will comes, that time only it will work, otherwise it won't work. Okay, so it won't work means it is going to display the previous result one. So the previous results are 0 and here also 0, here also 0. So when the first clock pulse, the outputs are this is LSB. So 0, 0, 0, 1. Have a look at this. Okay, right. So now I'm going to apply the clock pulse, second clock pulse. So when I'm going to apply the second clock pulse, for all the cases, JK values are equal to 1, 1, 1. Right. So now it is going to toggle the previous output. Previous output is 1. Now it is toggling means it is changing to 0. Now this 0 will comes here. So now this will work. Okay, because the clock is negative is triggering, so 0 is arrived. So now this is working means what it will do? It will is going to toggle the previous output. So previous output is 0. Now present output is 1. Okay, now this 1 will comes here. So it will not work because here negative is triggering. So this will produce the same result 1 is 0 0. So Q3 is 0, Q2 is 0, Q1 is now 1 and Q0 is 0. Okay, 0010. Have a look at this 0010 second condition. Then, during the third clock pulse, so during the third clock pulse, again it is going to toggle the previous output. Previous output is 0, now present output is 1. So here 1 will come. So this second, third, and fourth, it will not work. So it is going to give the same result. So same result means here 0, here 1, and here now this one. So 0, 0, 1, 1. Okay. So see here 0, 0, 1, 1. Fine. Now during the fourth clock pulse, it is going to toggle. So previous is 1, now it is 0. So this 0 will comes. So now this will work. So it is going to toggle the previous one. So this is 1, so 0 will come. Now this 0 will comes here. So now this will work out. So it is going to toggle the previous one is 0, now present one is 1, and this one will comes here, it won't work. So previous output is 0. So now the outputs are 0, 1, 0, 0. See, 0, 1, 0, 0. So have a look at this, 0, 1, 0, 0 during the fourth clock pulse. Okay, now fifth clock pulse. So here 0, so now it will be toggled into 1. So 1 means this won't work, and this won't work, and this won't work. So previous output says 0, 1, 0, now this is 1. So 0, 1, 0, 1. So the value is 5. So see here 0, 1, 0, 1. Okay, so likewise, it will work. Let us take the last combination, 15th combination. So 15th combination is it is 1, that is see Q3 is 1, Q2 is 1, Q1 is 1, and Q0 is 1. Okay, so now I'm going to apply the next clock pulse, that is a 0th clock pulse again I'm going to apply. So what it will do? It is going to toggle the previous one. So previous one is 0, 1. So 1. So now it will become 0. So this 0 will goes here, second one. So now second one will also will work. So it will toggle the previous output. Now this will become 0. And this 0 will goes here. And it will toggle the previous one. Now it is 0. And this 0 will goes here. 0 will come. So see, again it came to the initial state 0, 0, 0. 0, 0, 0, 0. So this is what our asynchronous ripple counter working is. Okay, and this is a timing diagram of asynchronous ripple counter. So first we need to draw the clock pulse. Here the circuit is working the help of negative edge triggering. So see here the negative edge arrow mark is there to each and every negative pulse. Okay, so this is the first pulse. This is the first one, second one, third, fourth pulse, fifth, sixth, seventh, and eighth pulse. Okay. So whenever it is starting and ending, we need to draw one vertical line. This line is very very important. Okay. Right. So during the first clock pulse, what is Q0 value? So during the first clock pulse, Q0 value is 1. So Q0 is 1, remaining all are 0. See, remaining 3 are 0. So all 3 are in the low level. So this is 1, 0, 0, 0. In the second condition, 0, 0, 1, 0. See, 0, 0, now this is changed into 1 and this is changed into 0. That is, when it goes to 1, we need to draw the signal like this. When it comes to 0, we need to draw the low level signal. So this is 1 and this is 0. Okay, that is, let me explain. First, we are supposed to draw the clock pulse with the equal time period. Once you have drawn the, this is a negative x, no? So here we are drawing the edge. So here we need to mark the dotted lines here. Okay, then it is q0, q1, q2, and q3. So what is the first condition? It is 0, 0, 1. That is q0 is 1. So for this condition, I'm going to draw. It is 1. Then q1 is 0, q2 is 0, and q3 is 0. So in the second condition, this will be 0 and q1 will be 1. So I'm going to draw the high level signal. Okay, remaining these are only 0, 0, 1. So likewise, we need to draw each and every class conditions. So this is what the working principles of asynchronous ripple counter. Okay, so this diagram is very very important. Okay, and the clock signal connection is very very important. And the truth table, then timing diagram. Once you have done this truth table, then the timing diagram drawing is very very easy. Okay, fine. And the next one is down counter. In the previous one we have seen that it is working in a upward direction. Now this is in a downward direction. Have a look at this. There will be a one small difference will be there. That difference is here they are using positive edge stickering. Just we change edge stickering only. Okay. So here there is no bubble, so it is working in a positive mode. So positive mode means first it is going to work in a downward direction. So first condition, let me clock is one. So this is clock and Q, Q3, Q2, Q1, Q naught. So during the first condition order 0, 0, 0, 0, 0. Okay. So now I'm going to apply the clock pulse value is equal to 1. So it is always JK always a high level. So 1 means it's a positive one only. So it is going to toggle. So toggle means this value is now changed into 1. So 1 means here positive it's triggering only. So this will work. So here 1 will come and here 1 will come and here 1 will come. So during my first clock pulse, first clock pulse, all four digits are 1, 1, 1, 1. Now I'm going to apply my second clock pulse. So what will happen? This will toggle up. So toggling means here it will change into 0. 0 if the coming means here clock is positive shading, so it won't work. So this won't work means remaining 2 also it won't work. So again the same output is going to be staying in the remaining 3 stages and the last output is 0. Okay, and third clock pulse. So here toggling will be happened. So now this is 1. So this is 1 means here toggling will be happened. So this is 0. And 0 means this won't work. So again it is 1. Again here it is 1. So now the outputs are 1, 1, 0, 1. Okay. So see this value was 15 and this value was 14 and this value was 13. So likewise each and every clock pulse the values are started to increase. So this is what asynchronous down. Okay, have a look at this. This is the truth table. See, first initially 4 zeros, then 4 ones, there is a 15, 14, 13, 12, it will go degrees like this. Okay, and the timing diagram, as per this truth table, we need to draw the timing diagram. See, the first condition Q0 was 1, so here positive is triggering, so when it is started to increase, at the time the output will be produced. So 1, 1, 1, 1. Okay, so then the next condition it is changed to 0 and this is 1, this is 1, this is 1. And again it is changed to 1, this is 0, 1, 1. Again it is changed to 0, this is 0, 1, 1. Okay, so likewise we need to draw the time. So this is what is asynchronous down. And there will be a drawbacks in the asynchronous counter. So what does the drawback means? That is in the propagation delay. Yes, because so the second flip flops have to wait for some time to get the clock signal from the first one. Okay, if it is taking 2 seconds time period to produce the output means, so this flip flop have to take 2 seconds time period to delay, and this will take another 2 seconds. So the next flip flop will take 4 seconds time period to produce the output. So see here, Q0 is producing the output is here, but Q1 is producing the output with some delay. Okay, so Q1 is producing the output is here, but Q2 is taking some delay. And Q2 is producing the output is here, and Q3 is taking some delay. But we need the output, all the flip flops have to produce output at the same time. If here output is changing means the same time all the output have to change. So that is the main drawback in asynchronous counter, that is propagation delay. Okay, right. Right. So I hope you guys understand the different types of counters and the working principles of asynchronous triple up counter and triple down counter. Okay. So we'll see in the next lecture regarding asynchronous counters. Until then, thank you.